So welcome back. And the topic today and also next week is a topic about a method which is extremely popular. It's going to be used as a stepping stone towards generative methods. Autoencoders is also a method which allows us to deal with unsupervised data. So if we look at CNNs and recurrent neural networks and feed-forward neural networks as the way we've been studying till now, we have normally dealt with supervised data, which means we have labeled data. Now, with labeled data, what we end up with is a problem where we often don't have that much data because it's expensive to label the data. Now, autoencoders can be used both for supervised type of problems, unsupervised types of problems, and they can also be seen as generative methods because we are going to train a network which can be used to generate new data. So it allows us to make a kind of a stepping stone towards our next big topic, which is generative methods. And also what we will discuss a little bit later with this acronym, VAE, variational autoencoders, is a topic which we will discuss after the Easter break. Now, today, we are also going to try to catch two birds with a stone. And we are going to bring in a very popular unsupervised learning method, which is called principal component analysis. And autoencoders can actually be viewed when we have a linear transformation as a linear autoencoder, which is then fully connected to principal component analysis. Now, principal component analysis and autoencoders, the way you have to look at them are as ways to reduce the dimensionality of the problem. So an autoencoder, what it tries to do is to find effective degrees of freedom, which you then can use to encode the information. Then you can decode the information and reconstruct your full data set. So what we are going to optimize with the autoencoders, but also in the principal component analysis, is something which we will call the reconstruction error. So I'm going to make these things a little bit clearer for you when we start looking at the mathematics of the principal component analysis. So today's lecture is going to be a lecture without much coding. We are going to look at codes for autoencoders next week. But today we are basically going to stay on the whiteboard and look at the mathematics of the principal component analysis and show that when we have a linear encoder, we actually recover the principal component analysis. The principal component analysis is, in a nutshell, a very efficient way to reduce the dimensionality of the problem. So what you essentially do with the principal component analysis is that you diagonalize what is called the correlation matrix or the covariance matrix. And then you keep only those eigenvectors which represent the largest eigenvalues, which then corresponds to the largest variance. And then you hope that these largest eigenvalues and their pertinent eigenvectors allow us to reconstruct the data we want to reproduce. So keywords now are: one, dimensionality reduction. We want to find what is called a latent space with effective degrees of freedom, which are powerful enough to describe the data with an error which we are satisfied with. That's one thing. The other thing is that besides that, we want to optimize the reconstruction error. So the optimization problem deals with the reconstruction error. So let's slowly go through some basic things first with the slides, and then we're going to dive into the mathematics because there is a lot of nice linear algebra when we are going to prove the connection with linear autoencoders and principal component analysis. Now, autoencoders, it consists of what we call an encoder, which you use to reduce the dimensionality. And that can be a set of neural networks. It can be a convolutional neural network, etc., etc. And then you have a decoder part, which is symmetric with the encoder, and then tries to build up the output, which you want to reproduce. So the building blocks, which we have seen till now, recurrent neural networks, convolutional neural networks, feed-forward neural networks, they can all be used in the definition of an autoencoder. So autoencoders are actually extremely powerful methods to reduce the dimensionality of the problem. So let's try to look at the basic steps. And today we want to catch two birds with a stone. So we want to do both autoencoders and discuss principal component analysis. So principal component analysis is an extremely useful tool to reduce the dimensionality. So if you can diagonalize the covariance matrix, and suppose that is 100,000 times 100,000, then you keep only the largest values of the variances, suppose 10, then you can actually reduce the dimensionality from 100,000 to 10 effective degrees of freedom. And if that describes your data, then this is your effective degrees of freedom. So at the end, what we want, if you want to take a bird's view on everything we're doing with machine learning, it's actually to reduce the dimensionality of a monstrously big problem. So keep this as a kind of overarching theme, dimensionality reduction. Okay, any questions? So I'm going to go a little bit through with the slides here, and then I'm going to jump into the whiteboard. So the textbook by Goodfellow et al. Is actually pretty good. Rashka has not so much, but it contains a brief introduction here. And then there are lots of nice examples on how to build AIEs in Keras or TensorFlow, etc., etc. Next week, we will discuss the codes. So I want just to go through the basic theory. So the way you can view it, I'm going to read a little bit from the slides. So it's a kind of repetition of what I said now. So they are artificial neural networks. They are capable of learning what we call efficient representations of the input data. And these representations are called codings and without any supervision. So that means that we can think of that, an autoencoder, as an example of unsupervised learning. And these codings typically have a much lower dimensionality. So I'm going to repeat this about the dimensionality again and again, so that you see that this is actually a dimensionality reduction method. So they learn to encode the input data into lower dimensional representation and then decode it back to the original data. So what we want is that this step, the encoding and the decoding, basically gives us the original data. And when we are reconstructing the data, which is the output of the decoder, the hope is then that the difference is as small as possible. And that's the quantity we optimize. So the way you can look at it is a way of learning the latent features or hidden structures of data. So when we are going to discuss the principal component analysis, that's why it's so nice to link these two. So instead of separately discussing principal component analysis and then later autoencoders, we do both, because the principal component analysis has a very nice geometrical way of viewing the dimensionality reduction. So you can build intuition by looking at principal component analysis. And you will be surprised that it's not a very difficult method. And it can be used to generative modeling. So they are powerful feature detectors. So when we say feature detectors, it means that these are the effective degrees of freedom we want to find. So every time you have a big problem, so like I often deal with diagonalization problems. And I diagonalize matrices of 1 billion times 1 billion with iterative methods. And what I will often see is that when I look at the linear combinations of the vectors, it's only a few % of them which matter. The rest of the coefficients are basically 0. So that's an example of effective degrees of freedom. So when you have diagonalized, you can say that some of the degrees of freedom are just irrelevant. And this is essentially what we deal with when we do any type of science. Yeah?
Would it be like in a singularity composite, the decomposition of the image, not only a few?
Yes, exactly. Actually, the elegant way of deriving the PCA is with the singular value decomposition. And you will see that today. So there is a statistical approach, and there is also what we call a geometric approach, which is a basic linear algebra approach with the singular value decomposition. So that's fully correct. And we are going to show that the linear autoencoder corresponds to the principal component analysis when we have a linear principal component analysis. So how does this work? So they're split into an encoder part, which maps the input X. So X does not need to be your input. This could actually be the output you want to reproduce. But just think of X as a quantity you want to reproduce. And there is a function F, which is normally called the encoder part, and that can be a neural network. And then this produces a reduced output, H, where we now have some weights. So this is the encoder part. And this could be a neural network, which are training. And then there is a decoder part, which takes this reduced dimensionality and then rebuilds via a new matrix V, and then it rebuilds the output. So the difference between X and X tilde is the one you want to optimize. So this means that a quantity like the mean squared error is something which we will encounter again and again. And the way you can look at it, suppose you have some numbers here, like the MNIST dataset, and you will see that in the coding example next week, when we are going to have an encoder, which can be a CNN or a feed-forward neural network, recurrent neural network. We are then trying to find an optimal representation with a latent feature. So this is the encoder part, and this is the decoder part. And then obviously the hope is that the reconstructed input is the one which is as close as possible to what you fed in. So if you're looking at the MNIST data, the input are the numbers, the handwritten numbers, and the output are the handwritten numbers, but then reconstructed by you. And the hope then is that when you find these latent features, the real hope is that this latent feature can teach us something about the system. Now, unfortunately, when you deal with neural networks, for instance, what often happens is that you have zillions of parameters, and then it's very difficult to say that this specific parameter refers to some specific feature. So that's one of the problems with neural networks. When you do a PCA, on the other hand, you can actually retrace these features to the explicit problem which you have. And if you're lucky, you can retrace that to the governing forces which influence a system. So like when I do science, I'm obviously interested in solving equations, but when I've solved equations, I want to ask, what does it mean? And how can I understand what I see in terms of the underlying forces which act on the system? So that's my obsession in life here. Actually, when I do things, I want to find effective and simple messages for why the system behaves as it does. That's what we want at the end. That's the ideal. So the hope is that these latent features is something which allows us to say something about the system. In most cases, it's not the case, unfortunately. But you can. What?
Even in autoencoders, you say that it's hard to use like nothing.
So with the linear autoencoder, you can actually, due to the link with PCA, you can actually try to find what it means. But when you have a non-linear autoencoder, it becomes much more difficult because you have so many parameters. Then you don't see the wood for the trees. So essentially, the encoder and decoders are typically neural networks since they can easily be trained with existing libraries. So one of the reasons why we spent so much time in the beginning here to remind you about neural networks, CNNs and RNNs, although many of you have seen it, is that these are basic building blocks which can be used in an autoencoder. So in general, the encoder can be written as a function G that will depend on some parameters. And I'm going to quickly skip a little bit some of the slides, and I wanted to actually discuss a little bit because we're coming back to next week about how we write a code for autoencoders using PyTorch or Keras. But now I wanted to focus a little bit more on the mathematics. Okay, so let's switch over to the whiteboard, if that's okay. So you will find a lot of the information here as well. So this is just about the kind of, let me just say this one before we move on. So what you typically will end up with is to optimize a function like this, where this x now represents your input, and the xi tilde is the output of the autoencoder. The difference between these two is going to represent what we call the reconstruction error. So obviously we want the difference between these two quantities to be as small as possible. And this is the function we will be optimizing. So what it means is that, so let me skip this one, but when we now look at the autoencoder, I'm going to show you the type of function. So this is typically the function which we are going to produce for our variables. And we want to optimize this difference, which in principle then means that we are going to, let me just set up the function here, is actually that we are going to minimize a function like this. So this is where I want to start now when we look at the whiteboard notes. So let's switch to the whiteboard and then look at the basic mathematics which we have to deal with. So I will most likely stay with the whiteboard for the rest of today's lecture here. So what we have, if we now set up the network, so we have some input x, oops, not that one. So we have some input x, which goes into this encoder part, and I'm going to write it like this. So this is the encoder. This produces some output, which I'm going to call for h, and these are normally called the latent degrees of freedom. Then there is a decoder part. And as I said, next week, we're going to look at how we do encode this using either PyTorch or Keras. And this produces an output, which I'm going to call for x hat here. So we're not going to specify what these x's are. I showed you one example where there could be the handwritten numbers between 0 and 9. That's an example of an input. We have an encoder, which then finds some effective representation, and then we have a decoder. So that means that what we are going to have then is that this h, which we see here, is going to be some function given by some function f, which then is going to depend on some parameters. So we're going to write this first as it will depend on the input, and then it's going to depend on some parameters, which I'm going to call WE. So this will be the weights of a neural network, for instance. And I put this subscript E because this represents the encoder part. So this is H. Then I'm going to set up an X here, which given this variables H, can then be used to reconstruct through a new set of parameters, which are then encoded in this WD. So you can think of WE, if this is now a feed-forward neural network, then what normally happens in an autoencoder is that these networks are symmetric. So you could think of you having less and less nodes so that you output some specific, say, dimensionality here, says you have 10 nodes. Then it will be symmetric where you start the decoder. And then at the beginning, like here, you could have, let's say, 1,000 nodes and 1,000 nodes here. You step this down with a given number of hidden layers. and then you encode the information in only 10 nodes. Then this is symmetric here with another 10 nodes. And the layers here are typically symmetric in the decoder with the encoder. That's a typical structure which is set up. So if you look at these equations here, these are the type of equations which we need to optimize with respect to. So the reconstruction error, which we are going to construct, reconstruction error, this is the quantity we want to optimize. And this is typically the mean squared error. And it's going to be given by 1 over n. And then I'm just putting a sum from I equal 1 up to n here. And then I have my x of I minus some x of I hat, which is the reconstructed error. This quantity is squared. And the way we would write it is as a 1 over n. And then I have the sum I equal 1 up to n. And then I have my x of I. And this is given by minus. And then I have these functions. If we now go back here, we have a function g and a function f. So it means that there's going to be a function g here, which then again is a function of f. So it's going to contain these parameters d. And it's also going to be a function which depends on this variable here, x of I. And this contains now the encoder part, like this. This is the function we want to optimize. So the optimization now is with respect to these parameters WD and WE. So we would then have the minimization problem for WD and WE of this quantity which we have put in here. And now I'm just going to write it like I equal 1 up to n. And I'm just going to put arrows down here of just plain laziness. Okay. Now a small digression here. So this is a small technicality, because what we end up, if you now think of these as in general, these objects, x of I, and this quantity here will be matrices. So in general, the xi, etc., are matrices. So from a technical point of view, what we end up optimizing is actually something which is called the Frobenius norm. Are you familiar with that? I'm just going to give that as a technicality here. So if you look at this equation here, what we are setting up now is an optimization, and I'm going to skip the 1 over n, but we are going to optimize a problem which looks like as follows. So let me just set up that properly here. We are going to optimize x minus this x hat, and this is the Frobenius norm squared. So this is a quantity which we can efficiently write as a trace of that difference. So this is the reconstruction error which we want to optimize with respect to the parameters. So how many of you have seen or remember the Frobenius norm? Okay, so that's unknown. So let me just show you what it is, okay? Because this is something which I can write out as the trace of this matrix X minus X hat transposed times X minus X hat. And when we optimize them, we are going to optimize this quantity here. And you can add Lagrangian parameters, because this is now going to be your Lagrangian. And then you can add constraints on the function here. And this is something you will see a little bit later today when we discuss the principal component analysis. So if you now look at the Frobenius norm, so let me just, since I could see that not many of you have seen that, This is the same. Suppose now that the matrix A is a matrix, a real matrix with dimensionality m times n. These matrices don't need to be symmetric because the number of features and the number of data which we have are not necessarily the same. So this is the same as a sum over I equal 1 up to n, and then a sum over j equal 1 up to n of aij squared. Have you seen this definition before?
Yes.
Say it again.
Related to some law.
No, this is called the Frobenius norm. Yeah, this. So F here is a so-called Frobenius norm. You can have 2 here, then it's the norm 2 of a matrix or a vector. So this is a special norm.
Related to if you want to regularize, right?
Yeah. So if you now think of the reconstruction error, suppose now your input is given by a matrix and your output is a matrix. So what you want with a reconstruction error is that all these matrix elements become 0, right? That's what we want. We want this x hat to be as close as possible to the input variables which we put in. So that means in principle that we want to drive in the optimization all these aij's to 0. So keep in mind that the overarching theme here is us wanting to optimize the difference between the output from the autoencoder and the input to the autoencoder. If this difference is small, that means that we have achieved a good reproduction of the data. And then we have trained a network which we can use to produce new images, for instance. Okay, you see the overarching theme? So let me just remind you of why this beautifully turns out to be the trace. So this is just a small mathematical detail. So if you look at the Frobenius norm, when you take, suppose I now take AT, actually this quantity is the same as a trace of the matrix transposed times A. So let's look at this quantity here of a matrix, and we just look at the matrix elements JK. Now, since we have the transpose, this means that since this is a matrix multiplication now, and since we are doing the transpose, I have to take the matrix elements not AJI, but AIJ. And this is multiplied by AIK. That's the matrix element. Okay, I'm just taking the transpose. Now, if I take the trace of this object, ATA, this is given by the sum over j equal 1, and then n, obviously, not m, but n. So let's do that. And of a, sorry, not that one, but AT times A of JJ. That's the definition of the trace. So if I do that, if I now just insert what I have put in here, then you can see that the trace of AT of A is equal simply to the sum over j equal 1 up to n, and the sum over I equal 1 up to m, and then aij squared. And this is nothing but the Frobenius norm of that matrix, F squared. So when we are going to optimize, what we are going to do then is actually to optimize the trace of this matrix product, where each one of them here represents the input and the output of the decoder. And we want that error to be as small as possible. Now, what is a connection with the principal component analysis? So let's try to look at that. So the principal component analysis, connection, principal component analysis, and autoencoders. And AES. So what is the connection here? So remember now that the new variables which we have, this x of I, is now given by a function which we call for g, which depends on these parameters h, but it has the encode, the decoder part, and then it includes this h, which is then given by a new function, which depends on the input x and the encoder part, like this. So what I could say now is the following. I can make a model. I can make a linear model. And this is the model which will allow us to make a direct link with an autoencoder and the principal component analysis. And this is where we are going to catch two birds with a stone. We are going to show how we can use the principal component analysis as a way to reduce the dimensionality of the system. And at the same time, we will show that the linear autoencoder is the same as a principal component analysis and a linear principal component analysis. So there's a one-to-one direct link here. So linear connection, let's set that up. So what is that? It means that this latent variable which we have, which is given now by a complex neural network with the input and these parameters, the encoder parameter, is simply given now by a matrix multiplied with x. So it's linear in the unknown parameters, simply because I have this WE to power 1. The next thing I'm going to say now is that this x reconstructed, and pay attention now that I'm not putting in vector signs or matrices. So this is something which we have to put in the right context. This is often stressing when you look at many textbooks on statistical analysis in machine learning, is that the author will typically say, it's up to the reader to figure out the context, whether these should be vectors, scalars, or matrices, or tensors. That's always a little bit irritating. But I take the same freedom here. Okay, so x now is given by this function g, which contains h and this wd. And we are simply going to set that up as wd times h, which means that now we have wd, we times x. So it's linear in the two unknown set of parameters. Okay, this is what we mean by linear. So that means that our autoencoder then is actually us doing a minimization, argmin, of wd and we of this quantity here. And now I'm just simply going to assume that these are vectors, so wd and w will be matrices from 1 up to n. And then I'm having x of I minus wd times we times x of I squared. This is a quantity I'm going to optimize. So when I say linear connection, this is what I mean. Okay? And you can make an autoencoder which looks like this. There is no problem. But this links directly with linear principal component analysis. And this is why we can actually catch two birds with a stone. And you can see that when we do a principal component analysis, which in principle is a dimensionality reduction approach, then we can think of this reconstruction error, which we have here, as a way to find the essential degrees of freedom. So I'm going to guide you so that you see that the PCA actually represents a reduction of the degrees of freedom. And that means that we will have a situation here where we not necessarily actually have a full case, a full set of degrees of freedom. So what I'm going to do now is first to remind you of a simpler method, which is called ordinary least squares, which doesn't reduce dimensionality, but it's going to serve us as a way to introduce the basic quantities. Okay? So let's now look at the proof of link between linear autoencoders and PCA. So I'm going to introduce some different parameters, and some of you have seen this before when you took FYS SDK 4155. So I'm going to define my input data, and I'm going to define them in terms of a matrix, X, and then the output which I want to reproduce is given by a vector Y. So this X is now a matrix of dimension n times P, and this Y is a vector of length n. So you could now think of this X, which is normally called the feature matrix, or the property matrix, or the design matrix in machine learning. This contains our inputs, and you would simply have inputs like x00, x01, and all the way up to x0p minus 1. So the columns represent features. So in case you're looking at, let's say, an example like credit card data, depth, then you could have that each column represents a feature like the age of the credit card holder, the occupation, education, etc., etc. So each column represents a feature, and then each row here represents then a data entry. So if you have 10,000 credit card holders, then the rows could then be the 10,000 credit card holders. So that means that we would have an x1, 0, and down the way up to xn minus 1 data points. And this continues all the way up to n minus 1 to p minus 1 features. So what we have then is that the rows are the data entries. And these columns, they are the features. So if you're looking at other data sets, like a way to classify, let's say, cancer, then each column could represent features like the size of the tumor, the perimeter of the tumor, the area, etc., etc. So columns are features, and the rows are the data entries. Then some of you have seen ordinary least squares. So who has never seen ordinary least squares? Okay, let me quickly remind you, because there we have an analytical expression. So our model then, which gives the data set y tilde, is then given by this matrix X times a set of unknown parameters. This is linear, and it's actually you optimizing, taking the gradient of the mean squared error between y tilde and the data you want to reproduce, this y. Then you can find, by taking the gradient, you can find an analytical expression for the parameters theta hat. These are the optimal ones. And that's given by the inverse of this matrix, X, times the transpose multiplied with Y. So this is ordinary least squares. That means that this Y tilde is actually given by X, or 1 divided by X transpose times X transpose times Y. Obviously, if this matrix which you have here is an orthogonal matrix, then clearly this is going to give the identity matrix. And then I will have the identity matrix, and then Y tilde is exactly equal to Y. But that's never the case. There's one important thing here. If we call this matrix for A, then this matrix has a property which is actually interesting. So it means that our Y tilde is given by A times Y. Does anyone remember what we would typically call this type of matrices? Or operator, if we want to use that word? So they are so-called idempotent and properties of projection matrices. So what we are doing now is actually we are projecting out using the column vectors of this matrix X. We are then producing an effective representation of Y. Obviously, if A is the identity matrix, then we have basically a perfect error, because then Y is equal to Y tilde. Okay? So you can read standard and ordinary least squares as a projection of the original Y. So you perform an effective construction of Y in terms of the column vectors of that matrix X. That's the way you would typically read it. Now then, what we would have then, in our case, for this specific case, if we now go back to the reconstruction error, it means that our reconstruction error, which is given by WD times WE, if we think of these as matrices, is now actually given by A squared, which again is equal to A. In this specific case, what I wanted to emphasize is that there is no reduction of dimensionality. So no dimensionality reduction. I'm dealing with the full dimensionality of the matrix A. So ordinary least squares is an instance of this autoencoder, linear autoencoder, but where we don't reduce the dimensionality of the problem. So we keep all the features. And clearly, if you're dealing with, let's say, some biological studies, and you want to retrace some specific properties to the DNA, then the DNA, there can be a million of features. And that means that your matrix, this matrix X transpose times X, will be a matrix of dimensionality 1 million times 1 million. Now, what could happen is that of these 1 million features which you have in the DNA of a specific type of, let's say, illness you want to retrace in a patient, perhaps only 10 of these 1 million features are those which matter. So clearly, if we are looking at ordinary least squares as a brute force method, there is no dimensionality reduction here. However, what we are having is something which now gives us a simple model for the decoder and the encoder. Because what we will have then is that the quantity we want to optimize, the mean squared error, 0 up to n minus 1, is going to be given by y of I minus y of I tilde, like that, squared. And this is something which we then can rewrite in terms of 1 over n, and then we have y as a vector minus this x times theta multiplied by y minus x times some theta. And in our case, this x here is kept as it is. There is no dimensionality reduction. Okay, so next step, singular value decomposition. So I promised you a chain of small mathematical arguments, okay? So let's look at the singular value decomposition, because that's the mathematical theorem which we are going to use when we now look at the principal component analysis. So this with the ordinary least squares was just a warm-up, where we have a connection between the encoder and decoder part in terms of the matrix which we are using in ordinary least squares. And here there is no dimensionality reduction. So let's remind ourselves of the singular value decomposition. So I used to say jokingly that this is actually my favorite algorithm, because you can decompose any matrix. You remember that if you have a matrix which has eigenvalues equal to 0, you cannot find the inverse, the determinant is equal to 0, etc., etc. But you can decompose. So you have something which is called the LU decomposition. That requires that the matrix is invertible, for instance. But then singular value decomposition theorem means that you can decompose any matrix, even if it's singular, as follows. So if I now take this matrix X, I can decompose that in terms of a matrix U, a matrix D, and a matrix V transposed. And I'm going to quickly set up what these matrices are. So the matrix U and the matrix V are orthogonal matrices. So U is a matrix of dimension n times n. It's also a matrix when I look at these expressions here. This is given by the identity matrix. And this identity matrix has dimension n times n. V is also an orthogonal matrix, but it has another dimensionality unless the dimension of X is the same. And this is also a matrix which has V times V transpose, which is equal to the identity matrix. But in that case, it's a P times P. And D contains the singular values. So lambda 0, lambda 1, down to some lambda P minus 1. And then it has the rest of zeros. So these are called the singular values. And obviously the zeros reflect the fact that your matrix can be singular. So you don't get rid of a singularity. It just, what the singular value decomposition theorem says is that you can always decompose even a singular matrix in terms of two orthogonal matrices. So these are called the singular values, and you can order them as you want. The ordering which we are going to choose is that lambda 0 is larger than lambda 1, is larger than lambda 2, etc., up to lambda P minus 1, which is larger than 0. And then we have a set of zeros. So as an example, this D could look like as follows. So 2, 1, 0, 0, and 0, 0. So this is a 3 times 2 matrix. Let me just say one more thing before we take a break. Okay. So these matrices U and V, they contain vectors which are orthogonal. So it's U0, U1, etc., up to UN minus 1. So these are the columns of that matrix. And the same with V, V0, V1, up to V of P minus 1. And since they are orthogonal, what we have is that U of I transpose multiplied with U of J is equal to delta Ij. And the same with V of I transpose multiplied with V of J is equal to delta Ij. So these are orthogonal vectors. And this is something which we are going to use a little bit later after the break to show that we can use the singular value decomposition to reduce the dimensionality of the problem. Okay. So these were just technicalities. So keep in mind now that what we have done with ordinary least squares is that we have showed that this decoder and encoder part can actually be written in terms of this matrix, but there is no dimensionality reduction. So in a certain sense, we haven't gained or we haven't obtained what we want to have effective degrees of freedom. Okay. So basic message, autoencoders, principal component analysis, effective ways to reduce the dimensionality of the problem. Okay, to take a small break, we do 15 minutes. I went a little bit over time, but I just want to set up the technicalities. And after the break, we are going to derive the principal component analysis theorem.
Skal vi bare vente litt, jeg skal bare stoppe den.
So I'm going to show the PCA theorem and the link with autoencoders a little bit step by step. So before the break, we looked at the standard ordinary least squares, and which then led to no dimensionality reduction at all. what we're going to do now is to look at the singular value decomposition as a tool to reduce the dimensionality of the ordinary least squares. And then we're going to link that with the reconstruction error again and the principal component analysis theorem. So if we now look at the singular value decomposition, so I'm obviously not proving the theorem, but I'm simply stating that we can singular value decompose any matrix. That's the strength of the theorem. And these matrices which we get, U and V, are orthogonal, and D is a diagonal one which then contains the singular values. And obviously, if your matrix is singular, there will be zeros. There is no way to actually avoid singularities. Okay, so these are the matrices. Let's just look at ordinary least squares and use singular value decomposition on that as a tool to look at how we can reduce the dimensionality. So let's bring back ordinary least squares, and the output, which we want to be equal to the target value, is then given by this matrix X, the input data, or the feature matrix, the matrix inverted times X transpose times Y. Now I can use the singular value decomposition. So what I'm going to write now looks extremely clumsy, but you will then see a route towards dimensionality reduction. Okay? So this is basically what we're going to do now. So let's now use the singular value decomposition. So I can actually rewrite this as a U times D times V of T. And then this is divided, and this looks like a horrible overcomplication. But the benefit is that we are going to decompose things in terms of the vectors of one of these matrices, U or V. Then what we have is a D transpose U of T, and then I have U times D or V of T. And this is obviously multiplied with V dt U of T multiplied with Y. So this looks horrible. So why is this guy doing this? This one translates into the unit matrix because these are orthogonal matrices. So if we now look at the denominator, this denominator is something which we can rewrite. And we can rewrite it in a simpler form. So let's just look at that. Now, there is one of these, what I normally call the hidden gems of linear algebra. So if you look at the two matrices, A and B, these are square matrices and invertible. And invertible. This is actually important. If they are that, then I can use a relation here which says that A divided by B is equal to B inverse multiplied with A inverse. And this is what I'm going to use to simplify the denominator. So keep in mind now that the denominator, in our case, looks like V of dt times D times V of T. This is a square matrix, and this D of T dt, when I calculate that one, that contains only variables which are non-zero by definition. So when I multiply D transpose with D, so D itself is actually given by what you see here. But when I take the transpose and multiply it with itself, I get a matrix which has only diagonal elements, and where all are non-zero. So D is invertible because everything is non-zero, right? Now, V and VT are also invertible because they are orthogonal matrices and they are square matrices. So what I can do now, if you now look at these calculations here, I can just break it up in two small elements. So I can say that V, nope, not that one, but V of dt of D of V of T, I can call this for matrix A and this for matrix B. And B is then composed of two new matrices. So if I now use that relation, that means that this quantity here is something which I can rewrite as V. Let me just write it properly here. So this would be V. So if I call this for B, then I would have V. No, sorry. Let me just do it correctly here. This quantity here can then be rewritten as d dt of d of v of t inverse multiplied with v inverse. Okay. Then I can take this one and apply the same trick on that one, because this is just the inverse of two matrices. And I can actually, by doing that, then I can show that this expression, which I have, u dt v of t, now reduces to v. So I'm using that relation with a over b, the inverses. And this is given by 1 over dt of d. And this contains v of t times v. And then it has dt of u of t times y. So this is now my y tilde. Now, in this case, I can use the fact that these are unitary matrices, now orthogonal matrices. This has dimensionality p times p. This has dimensionality p times p. This is also a matrix of dimensionality p times p. Now, the matrix U has dimensionality n times n. This one has dimensionality n times p. So that obviously fits when we are multiplying with this one. This one has dimensionality p times n. This one has dimensionality n times n. And this one obviously has dimensionality n, length n. So when I then multiply these guys, what happens then when you do the multiplication is that the dimensionality here makes sure that when you now multiply this d with this object, you get something which has length n times p. However, by the multiplication here, you get rid of all the zeros. So that means that the final product here is then going to be given by, it's quite easy to see that, as a sum over vectors from 0, but not to n, but only to p minus 1. And then I'm getting u of I, this is a vector of the orthogonal matrix, u of I transpose, and this is multiplying with y. Now, if the matrix X is a square matrix and it's invertible, then P is equal to n. And that means that what we have here does not represent a dimensionality reduction. Now, what you note here is that this is a matrix because it's an outer product of two vectors. That means that we have a matrix which now projects out components of y, and the projection is given by the orthogonal vectors in the singular value decomposition. So the PCA theorem, when we use the singular value decomposition, in a nutshell, PCA means that we want an effective dimension dim, which I'm going to call for M, which is either equal to or less than the dimension P. So P represents the degrees of freedom we have. Your matrix X has P features. So if you're looking at, let's say, the DNA in a specific type of illness, this number of features could be 1 million, for instance. And that means that your matrix, which you have to invert, is a 1 million times a 1 million. However, if you look at this projection here, what you want now is only effective degrees of freedom. So the question is now, how do we get these effective degrees of freedom? So you could simply just truncate, but Are we guided by something? And this is the question with the PCA here, and the link with the linear autoencoder. So what we want now, if you look at this expression here, we now want that this V, which we call for decoder part, and V double E, V for the encoder part, multiplied with Y, is now going to be represented by this I equal 0 up to some dimension, you can do that, of M, of these vectors U of I transpose, multiplied with Y. So you could now say that our encoder and decoder part is now represented by this singular value decomposition, and where we only have some selected degrees of freedom. So the standard ordinary least squares does not gives us a projection in terms of the columns of X, and there is no dimensionality reduction. Here, we could actually think of making a dimensionality reduction, but we need to be guided by something, okay? So essentially, what we are going to do now, suppose we have only one vector, and then we are going to call this for U0 of U0t. So that means that this is going to be equal to this quantity. Then the reconstruction error is proportional to us taking Y minus U0 of t multiplied with Y squared. Oops, this should be squared and squared here. That's the reconstruction error. So the hope then, if there's only one vector, which is a relevant degree of freedom, out of several thousands, then we get one reconstruction error. But we are going to add more and more vectors till we are satisfied. So how do we define satisfaction? This is what's coming now. And we're going to look at the basic elements of the PCA now. So what is this PCA? So if we now look at this matrix X, which we have defined as input data, this is a matrix of dimension n times p. We can write it in terms of the column vectors. So we would have x0, x1. These are different features up to p minus 1. And each one of these xi's, if we take one of these, it's just given by a vector of length n. So we have x0i, x1i, and all the way down to xn minus 1 of I. So I'm going to set in some definitions here. So the average of this vector xi, I don't put a vector sign in order to avoid clutter here, because this is the average. This is 1 over n, and then I have k of xk of I. So this is the mean value. That means that what I'm doing here, I'm just summing up all the elements in the vector and calculating the mean value of that specific column. So this column could, for instance, one of these columns could represent, for instance, the number of rooms a house has. If you want to correlate with the price of houses, where you have features like the number of rooms, number of bathrooms, size of the house, etc., etc. Then there is a quantity which I'm going to introduce now. So I'm going to introduce something which is called the covariance. And if I take two such vectors, xi and xj, if these are not correlated, the covariance and I and j are different from 0, then the covariance is 0. So if you have independent and identically distributed variables, and I is not equal to J, then the covariance is by definition 0. There is no correlations. So the covariance measures the correlations between the different features. So setting up the covariance matrix is something which is extremely useful. And the covariance matrix is the entry point to understand the principal component analysis. So if we now look at the covariance, this is defined as 1 over n, and it contains a sum over k, and I have xk of I minus the average value of that specific vector multiplied with xk of j minus xj average. This is a covariance, the definition of it. If the data are not correlated, this is automatically 0. So note one thing else, that what we have here is that we have a quantity xk tilde, which I'm going to define as xki minus x of I, the mean value. And later, or right now, I'm going to just replace it with x of I. So we call that we say that the data are centered. So this is a form of scaling, which many of you have encountered when you studied machine learning. And it's often used to avoid the influence of outliers in your data. So when you center the data by subtracting the mean value, the hope is that the fitting can go better because you're then putting less emphasis on outliers. So this is one of the standard scalings of the matrix of the data which you do before you start any machine learning algorithm. So when you typically now look at the covariance, instead of having xk of I tilde, I'm just going to use xk of I from now and on. So this is pretty common to have the data so-called centered. So if you now take two vectors, let me give you an example. So suppose this matrix X is given by x0 and x1, and that this is equal to a matrix with 3 elements in each column. So we have x10, x20, x01, x11, and x21. So this could be our input data. Then, when we calculate the covariance of this quantity, if we now look at it more closely, so this is the covariance, and I use that formula, which you have on the top here, of x0 and x1, this is going to be given by 1 over 3, because I have 3 data points in each. And when I just multiply here, I get x00, x01, plus x10, x11, plus x30, multiplied with x21. If you now look at this, this actually reads as follows. So if you look more closely at this expression, so let me just wait a little bit so that you get time to admire this last equation here. If you look at this one, we can actually rewrite that one as the inner product of this vector multiplied with that vector. So this expression here is the same as x00, x10, this is x20, so this is just x0 transpose, multiplied with x1, I'm just putting vector signs here, 1, x11, and x21. So we can actually rewrite this covariance for this specific example of x0, x1. This is actually given by x0 transpose times x1 divided by 3. So in general, I'm going to define a covariance matrix, and I'm not going to use this symbols x0 and x1. So this is called the covariance matrix. And this is something we would label as covariance of x. And this is going to be given by 1 over x transpose times x. And we have seen this quantity already in ordinary least squares. And we can actually link this quantity here also with a singular value decomposition. If you do the singular value decomposition, you get immediately the eigenvalues of this matrix X, transpose times X. And I will show you how that comes through. But the covariance, let me bring in some further elements of statistics. If you look at this quantity here for just the two vectors, so the example which we have now with x0 and x1 as the only two vectors which define the covariance matrix. So in that specific case, the covariance matrix is given by 1 over n. And what I'm having now is the inner product of x0 with itself. And then I have x0 transpose times x1. Now, these are symmetric, so I could actually, I could write it equal to the other non-diagonal one. So the covariance matrix is always symmetric. So if I look at an element like this xi transpose times xi divided by n, if I write this out, this is the same as, in our case, xki, and I'm summing over k here, of I squared of 1 over n. And in principle, since I'm using this centered matrix elements, it's actually 1 over n, and k of x of ki minus the mean value squared. This quantity has a name in statistics. Does anyone remember that name? Yeah? That's the variance. So the diagonal elements are the variances. Now, if there is no correlation between, if these are independent and identically distributed variables, then the non-diagonal elements have to be equal to 0. You can prove that. So I'm just stating it here. And that means that your covariance matrix is diagonal, and along the diagonal, you have only the variances. So this quantity which you see here is just the variance sigma I squared. So that's an important property here. Now, you can introduce later the so-called correlation matrix, and some of you are probably familiar with that. But what the PCA is doing, so now I am just anticipating, I'm stating the theorem. You keep only the largest variances, which are the largest eigenvalues or the covariance matrix, because you believe that those are the most important features. And then you truncate accordingly. So in principal component analysis, suppose instead of just a 2 by 2 matrix, you have a 100 by 100 matrix. And if the first 10 largest eigenvalues, which are actually the variances, if they sum up to, let's say, 90%, and that is your cutoff, then you will say that the 10 first eigenvalues represented by the largest eigenvalues and the largest variances are those which I want to keep. These are the most important degrees of freedom. And that's how you truncate. That's the PCA in principle. And you can see that in the different examples here, how you could actually make a truncation in terms of relevant degrees of freedom. So what I'm going to do now is to anticipate a little bit of the discussion by looking at a simple example given by this one, a 2 by 2 matrix. So let's just make up an example, and this is what you will find in the Jupyter notebook here. So let me just switch to that one and show you a simple case, which hopefully can allow you to make some intuition, a deeper intuition about the what the PCA is actually about. So let's scroll down a little bit here. This is just what we talked about in the beginning. And let's try to build up some intuition about the PCA. So what I'm setting up now, if you look at this example, I'm setting up by hand now a 2 by 2 covariance matrix, like the one you saw on the whiteboard. And I'm simply stating that the first element is 4, the second is 2, that the non-diagonal and the variance of the second element is equal to 2, right? And I have 1,000 data points, 10,000 data points, sorry. So I'm using that to set up each vector. So each vector has 10,000 data points, and the first vector has a mean value of -1, and the other of +2. So I'm setting up a vector of length 10,000, and then I want a covariance matrix of 2 vectors, okay? This is exactly the example which I put on the whiteboard. And here I'm choosing a multivariate normal distribution. Multivariate because I have 2 vectors now. And then I'm generating the data. So let's just generate the data here, okay? This is pretty straightforward. So the first step, as I said, is to center the data when we're looking at it. And this is something which I always like to use pandas. So I center my data. If you use scikit-learn, which is a famous library for machine learning, you will actually have all this functionality baked in. But here I'm doing by hand what we put on the whiteboard. Then I have centered data, and I'm going to calculate my covariance. So I print the covariance matrix, as you can see here. So I have 10,000 data points. I forced it to be 4 and 2, but since I don't have an infinity of data points, I don't get exactly 4 and 2, because I'm drawing numbers randomly from a pseudo-random generator, and I'm calculating the mean values, etc. But you see, I don't get exactly what I plugged in, simply because I have, if I were to increase the data set here with, let's say, 1 million, then I would get something which is closer to 4 and 2. But this is what I'm feeding into the random multivariate normal distribution. Does that sound okay? Because we are always dealing with sample mean values. And when we have a limited number of data, you will never recover the true exact mean value and the true exact variance. But now I'm doing this, and let's make a plot. Because what I'm plotting now are actually the 2 components. So these are all the 10,000 points, okay? I have vector x1 and x2, the 2 vectors. And I'm simply plotting their components. So if you now wanted to do a dimensionality reduction, you see that in this specific case, you wouldn't be able to do that, because you have to account for both degrees of freedom. So, however, if I now go back, let me see, there was something. Let's go back here and make a more extreme case. So suppose now I say that this is 10, and this is very small, 0.1, the non-diagonal ones. So that's the covariance between vector x0 and x1. I also make this one small. Okay? So let's see what happens. What do you think would happen? Exactly. So let's just do that. Then I just print it. And now we plot it. So this example here is actually true. You see this? And now I could make an approximation. I could say that, hey, in the y directions, there is not big variation. The variation is in the x direction. And this is the one I want to account for, because the y direction is basically flat and looks like Denmark seen from the sea, or the Netherlands seen from the sea. No, by the way, you don't see the Netherlands from the sea because it's below sea level. So this is probably more Denmark seen from the sea. Sorry. Anyone from Denmark or Netherlands? No, okay. Actually, the Netherlands being below sea level is probably why the Dutch people are the tallest people on average in the world. They are actually. It's a very interesting fact. I don't think they are correlated. Anyway, you see the basic message here? So what we have here is a case that now, if you look at this correlation matrix, if I diagonalize it, if I take and diagonalize this correlation matrix, you see now that one of the eigenvalues is pretty large. And it's close to the value which we had for when we put up the covariance matrix here. We wanted it to be 10, and the non-diagonal one is very small, which means that these two don't mix much. And this is what we see here. And then it means that the eigenvalues, we could now say that since this eigenvalue, which we have here, this is actually the variance of one of the features. And what I could say now is that if I add these two, this is a feature where I could say now that, hey, I could say that the largest eigenvalue is the one which is a dominating feature. Because when I'm going to describe this system, this is actually the one where I have the largest variance. And this is the x-axis, which then represents the largest variation, and which will be relevant for our studies. You see that the other vector is almost orthogonal to this one. So what I could say now is that I can skip that by simply looking at the eigenvalue here, which is very small. I could say that if the variance or the eigenvalues of the covariance matrix, when it's less than, let's say, 0.1 or something, I skip that degree of freedom. And then I make an approximation where this one represents the effective degrees of freedom. So instead of a problem which has a dimensionality 2, I'm now reducing it to a dimensionality 1 problem. I obviously make a small error because there are variations here. So if you have this little example in mind, then you see the basics of the PCA. So the PCA is essentially finding the largest eigenvalues because they will probably represent vectors where you have a larger scatter in the variance. And that means that these are features you need to take into account. And then we neglect the other ones. That's the essence of the PCA. So let's now derive the PCA theorem. I mean, one thing is just to state these things by examples, but we need also to derive them, okay? So you have the basic picture, and then we just move over to back to the whiteboard. Okay, so what we have is this covariance matrix, and we need to make some further analysis now. So with the singular value decomposition, there is actually some interesting mathematical features which we're going to use. So we have stated now that this covariance matrix, X, which measures the degree of correlations between the data sets. Actually, this is a small digression. One thing which is very convenient, if you can calculate the covariance matrix, so just keep in mind that if you have many, many data points, this becomes heavy. So if you have 100,000 data points and 100 features, this becomes a heavy calculation. Because if you just look at the case with the 2 and 3, so we have 3 data points, then what you have is 1, 2, 3 operations, multiplications, and then 2 additions. And if you have, instead of just 3 here, you have 100,000, and you have 100 features here, the covariance matrix becomes expensive to calculate. So this covariance matrix, if we now look at it, we have defined it as X transpose times X. And let's bring back the singular value decomposition. So SVD again. Because if we have performed a singular value decomposition, we have the eigenvalues immediately. And that is really nice. We don't need to diagonalize it when we have done the singular value decomposition. You would diagonalize it because diagonalization is cheaper than performing a singular value decomposition. So if we now insert that one, what we have is that the covariance of X is then equal to 1 over n, and then I have a V of D transpose times U of T times U times D times V of T. Here we use the orthogonality. So that means that this is 1 over N of V of dt of D of V of T. So what I do next now, I multiply with the matrix V from the right. With V from the right. So what we get then is the following. I have the covariance matrix, which we have defined. I'm just writing it like this, multiplied with V, and that is equal to 1 over N of V, and then I have D squared dt, which is the same as D squared, multiplied with VT, multiplied with V, and that's equal to the identity matrix. This matrix here has dimension P times P, so that contains simply the singular values, all the way down to P minus 1 squared, like that. If we now look at this one, we also remember that V is given in terms of the column vectors, and they are orthogonal. So V1 up to Vp minus 1. So if I now just look at one of the components, just one component, so if I take instead the matrix V, I just take a vector, V of I. So that means that I would have a covariance matrix times a vector V of I, and that is equal to one of these eigenvalues, lambda of I squared, the singular value squared, multiplied with V of I. So what is this? This has a name in linear algebra. What kind of equation is it? Yeah, that's an eigenvalue equation. So if you have performed the singular value decomposition, what you have then is actually the eigenvalues of the covariance matrix. They are given by the singular values. So that means that the singular values, since when I diagonalize this matrix, diagonalizing that one gives me the variance. So it means then that these lambda i's, the singular values, are equal to the variances divided by a factor of n. Okay, so that's pretty neat. So if you have performed a singular value decomposition, then you have the eigenvalues in terms of the singular value composition, singular values squared, and they are the eigenvalues of the covariance matrix, which then are also the variances. So it means that this lambda i's, if I now look at it, so this lambda I squared divided by n is equal to sigma I squared, which is the variance. And they are obviously linked with a given eigenvector. Now, what you could do, however, is to diagonalize the covariance matrix. If you diagonalize it, you should get the same eigenvalues. Okay, I'm not going to do that because a diagonalization, I can do that. Okay, so let's just do the standard diagonalization. What that means when we diagonalize, we assume then that there is an orthogonal transformation which exists, ST, which is S times ST, which is equal to this one, which is so that if I multiply my covariance matrix X, which has non-diagonal matrix elements, this is going to be equal to the covariance of Y, which is diagonal. And that is equal to just sigma R0 squared down to sigma P minus 1 squared. You can actually show that this is the case, because now I have assumed that there is a transformation of my matrix, which brings my matrix to diagonal form. And you know that these are normally called similarity transformations. We change the vectors, but the eigenvalues stay the same. So we can find the eigenvalues by simply setting up a diagonalization problem. And this matrix S has a set of eigenvectors, which are orthogonal. So it's again an orthogonal matrix. So that means that all these guys here, the P minus 1, they also obey the orthogonality relation, which is equal to delta ij. Now, what we are going to do now is actually to assume that we can truncate the total variance by simply setting up a cutoff. So in the PCA, what we do then, we set a cutoff on total variance. Total variance. So if we take the total variance, this goes up from I to 0 up to this P minus 1 and sigma I. This is the total variance, sigma squared total. But we are going to set a cutoff where we now have a variable m, which is smaller or equal than P, the total dimensionality. And we sum from m minus 1 from I equals 0 to sigma I squared. And this is equal to a, or less than equal, a cutoff, which we choose. So this cutoff could be so that we recover, let's say, 95% of the total variance. Now, if you use scikit-learn, for instance, this is one of the parameters you would have to feed in when you use the principal component analysis in scikit-learn. So you could now think that when you look at these eigenvalues, if you go back here, you could now think that 95% of the variance is included in the 10 first eigenvalues or singular values. And then you just leave the other degrees of freedom out. So if you go back to that simple example, the 2 by 2 example, where we plotted the distribution of the points, then you saw very clearly that if I have a large eigenvalue and the rest is small, it means then that there is a scatter in one direction, and in the other direction, there is basically no variance or no variation. Variance is actually the variation around the mean value. And then we could then use that as an approximation. But just keep that figure which we had in the Jupyter notebook in mind, this simple example, because that simply reflects what we are doing now. Then, and this is something which we would have to conclude next week, is that now we are going to assume that we have only one vector. So the PCA theorem with a statistical analysis. So we assume now that there is only one vector, y. So y tilde, the reconstruction is given by S0 times y. And then this vector S0, actually, it's not S0. Sorry, I was wrong here. It's going to be given by S0 because it has to be a matrix, transpose, times Y. This is the original data. So that means that and this S0 is so that it's orthogonal. And then the reconstruction error, which we make, is then going to be given by the norm 2 of y minus S0 times S0 transpose times y. And we want that one to be smaller or equal than some epsilon, which is a small number. So what we're going to show next week, so in order to fulfill the theorem, is that this is going to lead to that the eigenvalues are given by the eigenvalues of the covariance matrix, and that these are then the eigenvectors which represent those degrees of freedom. And we can then, using Lagrangian calculus, we can then reconstruct all the vectors of that decomposition. And you will see that some of the eigenvectors then are going to represent variances which are small and smaller. So we can make a truncation and where we simply say that there is only a limited set of vectors which matter. And that goes back to that image which we saw. So next week, we are going to start here, and we are going to show what the eigenvalues are. And the eigenvalues are going to be the eigenvalues of the covariance matrix. And we can gradually build up all vectors of the transformation matrix, which gives us the eigenvectors of the covariance matrix. So this equation which you see here, you can then obviously diagonalize, and you have all the eigenvectors. Or we can construct all these eigenvectors by requiring that the reconstruction error is as small as possible. And this is the proof of the PCA theorem. And pay now attention to the connection with the autoencoders, the linear autoencoders. This is going to be given by the decoder times the encoder. So if I have a linear relation, I can then interpret this matrix as a product of these two matrices. This is the link with the PCA and the linear autoencoder. But in general, people don't use linear autoencoders because they are too simple. Because if you have a neural network, this is quickly a nonlinear optimization problem. So next week, I'm going to finish the theorem here, and we are going to look at the code examples and how these autoencoders actually behave and how we can actually encode them in an efficient way. So today, I just wanted to establish some of this basic mathematics so that you hopefully see the wood for the trees. Any questions before we stop and take a small break and then just move on to discussions of projects? Okay, I'm going to stop the recording now.